Hi, AP Physics students. Today we're going to talk about projectile motion, and you should be using the notes that you received in class. You'll see that the notes start at 2.1, which is vectors. Go ahead and review that when you get a chance, but I'm under the assumption that you are familiar with vectors and remember what is going on with vectors. We will touch on vectors later on in the course a little bit. They do play in projectile motion a little bit, but review that, and let's get talking about what a projectile is. In this, we're going to basically be looking at it at the honors level. We define a projectile as any object that's affected only by acceleration due to gravity. Basically, anything that's airborne, that's no longer getting pushed, that has no thrust, that has no engine, no jet, anything like that. If something's flying through the air and the only thing pushing on it is gravity, we refer that to a projectile. I do want to note that this includes things that are just falling down. A falling object is also technically a projectile. We talk about acted on by gravity. The acceleration due to gravity in this course, we're going to use 9.8 meters per second squared. Note that in honors physics, we use 9.81. The AP uses 9.8. We're going to use what AP uses, not what the honors regents uses. And just information about a projectile, anything that is projected, anything that does have some sort of horizontal component is not just falling straight down. The path of that projectile is always going to be the same thing. It's going to be a parabolic arc. So looking at this projectile, we call the arc or the path that the projectile takes while it's going, we call that its trajectory. And when you look at the trajectory of a projectile, I already said it was a parabolic arc. You can see this diagram. This is in your notes. The dotted red line would be the trajectory. That is that parabolic arc. Notice that I put the velocity vector on here, velocity initial. You'll note that the trajectory of the projectile and the velocity vector, they kind of split apart after it starts. And that's really important because the velocity vector is acting at the point and the trajectory immediately comes off of it. When we're talking about the trajectory of a projectile, there's two things that affect it. The first thing being the angle of the angle that it's launched at. The second thing that affects it is how fast it's going initially. So if you're trying to figure out where a projectile is going to go, its trajectory, you're going to look at the angle and its velocity. This is, of course, neglecting any impact of friction. We will talk about air resistance, but we're going to talk about that when we get into forces. So this is just angle, initial velocity, and this is how we're going to figure out the path of a projectile. When we talk about projectile motion, the whole concept behind projectile motion is understanding this independence of motion. We have objects that are moving vertically and horizontally at the same time. And if we want to be able to put together and figure out how the object's moving, what we have to do is we have to do analysis on each one of these motions separately. So we're going to do analysis on the vertical section, and then we're going to do the analysis on the horizontal portion of it, but the two are not going to impact each other. You can track where they are in time, both horizontally and vertically simultaneously, but you would just sort of kind of put that back together like an XY coordinate. So independence of motion, horizontal, vertical, the motions of each, they act independent of each other. This is the key most aspect of any sort of projectile motion concepts. When you talk about the vertical motion, this is the up and down. It acts under the acceleration due to gravity only. It's just like a free fall scenario. So we practice that vertical problems about something launched up or something dropped down. The vertical component of a projectile just acts exactly like that. The problems are perfectly the same. The horizontal has no acceleration. Acceleration due to gravity acts vertically, so you have that vertical component. Whatever you're moving side to side is not impacted by how you're moving up and down. So it has no acceleration. All horizontal motion here is going to have a constant velocity. And this is what I mean when I say independence of motion, because what's going to happen is that our vertical and our horizontal components here, they're going to be analyzed completely separately. So let's look at each one of these motions in turn. So looking at the vertical motion, our acceleration due to gravity is constant. It's always a negative 9.8 meters per second squared. We give the symbol G for it. And in this class, we're going to use the convention that down is negative and up is positive. In general, that's how we're going to do. We can look at it specifically question to question, but in general, down will be negative in this class and vertically up will be positive. When you have an angled projectile, if you want to find out what the initial velocity vertically is, you have to take the vertical component of it. And this is where we get the vectors portion of it. So you might have a velocity, say like 50 meters per second, that's launched at an angle of 30 degrees to the horizontal. That has a vertical component and a horizontal component that goes along with it. So you have all the vertical components, they're going to get the subscript y, and that is our convention for using our vertical component subscripts. When we talk about this vertical motion, and I already mentioned this, it is exactly identical to the motion of a freely falling object. And the vertical component of velocity will change with time. And it's going to be 9.8 meters per second less every second. And we're only going to use our kinematics equations to do this. So you have your 3 kinematics equations that we've learned. And we talked about these in depth, so I'm not going to really go through them again. But here you can see them. We have our 3 sets of kinematic equations. They work and can be used to determine all the vertical motion. You need those because of the vertical acceleration due to gravity. So you can't use velocity is equal to distance over time. You have to use an equation that takes into account the acceleration that it undergoes. Horizontal motion, on the other hand, is much, much simpler. Acceleration is always 0. So as soon as we know the initial velocity horizontally, we can figure out everything from horizontal components of position and time. It doesn't change, so since that velocity doesn't change, we're only going to be using this equation horizontally. Just velocity is equal to change in position divided by time. So that is the only equation we're going to use in the horizontal motion. Vertical, use the 3 kinematics. Horizontal, you're just using v equals d over t. So let's take a look at each one of these independently. When we look at projectiles, there's 2 major sorts of types of projectiles you can have. Either projectiles where you're launching the projectile and has initially just a purely horizontal angle. We call those horizontal projectiles. And we can also look at ones where you're angling it at some angle to the horizontal, and we call those angled projectiles. So let's talk about the horizontal projectile. Because if you were to launch something horizontally, it's going to have a vertical component after it's launched, but initially, it's not going to have any vertical component. So you're looking right here at this term, velocity initial, in the vertical sense, is going to be 0 meters per second. Velocity in the horizontal direction is going to be constant. And the acceleration is going to be in the vertical direction, negative 9.8 meters per second squared. Now, if you're looking at your notes, you'll see down below this, you have an example. I want you to try this example, and on the next page or the next slide, you're going to be able to input your answer. The following slide is just the answer, and then the slide after that is me solving it. So I want you to try it, then you could check against my key, the next slide, and then if you still don't understand how it's working, you can watch the following slide and then see how I solved it myself. After that, we'll talk about projectile motion. So go ahead, try this problem, and then we will meet back up again in a couple slides.